Welcome to Chapter 7. In this chapter, we're going to discuss numerical linear algebra. In Chapter 5, we discussed the finite element method. In Chapter 6, we discussed the finite difference method. In both cases, we saw that we eventually reached a step where we have to solve a system A, U equals F, a linear system, where A is a matrix, which is perfectly known, F is a vector, which is perfectly known or can be computed, and U is the unknown. U is a vector approximating the solution, and that's what you're looking for. So you need to solve a linear system. Now, many of you are probably thinking, that's really not a big deal. Come on, I'm a straight A student, valedictorian of my school, I went to class prepa, I really ranked really top, and I got to Central Supélec. I'm not going to be scared by a linear system. That is a good thing. However, I would like to emphasize that we're not talking about a linear system that you're used to. You're used to 3 by 3, 4 by 4, 10 by 10, but the kind of linear system we're going to deal with here is going to be huge. The reason why it can be very large is because this discretization step might have to be very small if you want a good approximation of your solution. In other words, J, the number of nodes, or J squared, will be very large, which will lead you to a very large linear system to solve. Now, this will cause a lot of problems in terms of complexity, in terms of computation in general. And we need to have an efficient strategy for solving linear systems. So this is something that we're going to address in this chapter. We're going to see how we can solve A, U equals F, or if you prefer different notations, AX equals B. To solve linear systems, we will see two types of strategies. The first one is what we call the direct method, while the other one is called the iterative methods. Direct methods is basically what you're used to. You decompose your matrix into the product of two matrices, B and C, and then you replace the system AX equals small b by BY equals small b and capital CX equals Y. Now, when you do this, you can choose, of course, an appropriate B and C. Very often, you choose LU, which is a decomposition that is basically based on the Gaussian elimination. Just to go quickly here, I would say the direct methods is what you're used to with the Gaussian elimination. The other type of strategy that we can put in is iterative methods. Now, iterative methods is building a sequence of vectors xn that will converge to the vector x that is a solution, and this solution, to ax equals b. We will see a few examples, Jacobi, Gauss-Seidel. We'll also talk about the conjugate gradient. Okay, so that's one thing we want to do, solving linear systems. And we'll see direct methods and iterative methods. Now, to do iterative methods properly, we need to talk about iteration matrices. So we're going to talk about that. And these iteration matrices will also be useful in the next chapter when we will discuss parabolic PDEs. Now, if you remember what we discussed when we talked about the finite element method, we talked about conditioning of a matrix. There was a situation where we had a vector B on the right-hand side that was changing slightly, and all of a sudden we saw that we had a large change on the solution. And that was a problem, we mentioned it, and we said we would come back to it in Chapter 7, and of course, well, that's when we're gonna address this. That will be called conditioning of a matrix. And we'll see that in the conditioning of a matrix, we can talk about, we need to talk about the eigenvalues, so that's the spectral properties. And again, computing the eigenvalues of a matrix is not something that will sound difficult when I say it. However, if the matrix is really large, then computing the eigenvalues of this matrix will require some strategies. Okay, so these are a few important things that we'll need to address in this chapter. I'm going to tell you how this chapter is organized. So we're starting this chapter by this introduction that you're currently watching, after which we'll have a first section on the norms of matrices. And this first section will be composed of 3 videos. The first one will be about the definition of norms of matrices. Many of you already know this, so you can probably skip it or actually go in fast forward through it to make sure that you know everything there is to know about the definition of norm of matrices. Then in a second video, we will discuss the stability of the finite difference method matrix for the Laplacian in dimension 1. That is an outstanding proof that we had to do. So that's something that we did not prove in chapter 6, and we said we would do that later. Well, now is a good time to do it. That will be the second video of section 1. And the third video of section 1 will be about conditioning of a matrix, and we will discuss this problem where obviously we need to characterize the situation where a small variation on the right-hand side can lead to a large variation of the solution of our linear system. The second section of this chapter 7 will be devoted to spectral properties, in other words, eigenvalues. We will discuss a theorem, the Gershgorin circle theorem, to find where these eigenvalues can possibly be located. And then we will discuss a method to find the possible largest eigenvalue in absolute value, and that will be the power iteration method. That will allow us to find this largest eigenvalue that will be called the spectral radius. So that's will be section 2, composed of 2 videos. Section 3 will be 1 video about iteration matrices. And then we will finish this chapter by 2 videos for section 4, and that will be solving linear systems, and we will discuss the direct method and the iterative methods, which of course are of quite large interest, considering that in chapter 5 and 6 we ended up with a linear system to solve. So we're going to see all these strategies in this chapter 7. Let's join me now to go to the first video on the norm of a matrix and the definition of it.